Hello, students. I'm getting ready now to do a demonstration so that you can see how to do calculations with really large and really small number, and especially how you can use the E notation that matches the E key on most scientific calculators. So in front of me, I have two examples of scientific calculators. One, an actual device that's cheap, very affordable, the TI-30XA, which is dedicated to doing these calculations. Or one could also do these calculations on a calculator app on a cellular device if that device is fully featured. And we're going to be looking for a key that has two capital E's side by side. And on mine, it happens to be right next to the 1. So what am I talking about? Well, many of us have probably been taught how to do scientific notation. We might have written, say, the number 1 million is 1 times 10 to the 6th, which, of course, is the same thing as a 1 followed by 6 zeros, or a million. Or perhaps we wrote 1 times 10 to the 9th, and when we wrote that out, that's a 1 followed by 9 zeros, a billion. Well, that's all very well and good, but in point of fact, at higher levels, we tend not to use a multiplication sign. When we do multiplication, we tend to have items that are right next to each other, or perhaps in parentheses and right next to each other. And oftentimes we don't bother to even use it to write this. And the reason is because, of course, the multiplication sign looks like the variable x, and that's potentially confusing. So what do we do instead? Well, what we want to do instead is we want to use a notation that looks like the way we put it into the calculator. And so as mentioned, many of these calculators have a function. It's called, it's got a little two capital E's side by side, just like that. And that's for engineering, for exponents. And that's what a lot of chemists and physicists and engineers and the like use. And so how would we write it? We would write, instead of 1 times 10 to the 9th, we would write 1 little capital E and 9. The way we put that into calculator is real straightforward. It would be 1E9, just like that. And as you can see, for that particular number, there's room to register it on the calculator. Let's do the same thing with the calculator out of my scientific. Can I do the same thing? Yes, I can. 1E9. Now notice in each case, it only took me 3 keystrokes, 1E9 to put it in there. Now compare that with 10000000000. Well, we can just barely fit that in with this one. We could do the same thing with this one if we wanted to, but we just barely fit it in on the scientific calculator. And the moment we start adding more zeros, well, lots of luck keeping track where the zeros are. And of course, every time we press a key, there's a chance we'll make a mistake. We start looking at really small or really large numbers and we have many zeros. If we miss just 1 0 when we enter into the calculator, well, we won't just be a little bit off, we'll be quite a bit off. In fact, we'll be at least 10 times off and maybe more than 10 times. So what I'm suggesting to you is that not only is it easier for me to go 1E9 to put that number in there, 1E9, not only is it easier, takes less time, less likely to make mistakes because you're putting in zeros, but it's exactly the way we can write it. So in our activity, the bright line spectrum, we have a number. And again, I'll write it the way I'd like you to write it. 2.997 E8 meters per second. Of course, if you wanted to, if you're absolutely determined to, because you just don't like to give up the way you've gotten used to doing things, you could go to all this trouble. 299,70000. And of course, if you wanted to, you can put that number into a calculator with that many keystrokes, or the same thing here. If you are absolutely determined, you can put them in that way. But again, every number you push, every time you push a key, that increases the chances that something bad will happen. Wouldn't it be much better to go 2.997 E8 like that? Because I get the same result. Wouldn't it be better just to go like 2.997 E8 and I get that result? You know, I mean, it's easy. It's easy that way. So maybe you're not convinced. And if you're dead set on putting in all the zeros by hand because that's what you trust, because that's what you're used to. Hey, I sympathize with you. But let me also be honest with you. A time is coming very soon in this class where writing numbers out becomes very impractical. For example, we're going to start using this number. This is the mole. This is the name we just give for convenience to this very large number, which is 6.02 times 10 to the 23rd power. If we were going to write this number out by hand, this is what it would look like. Don't blink. Don't breathe. So we're trying to do this all in one step. 1, 2, 3, 4, 5. 1. There it is. 1 mole. Sure took me a long time to write that out and real sloppy and quick like with all those zeros. And it would never be practical to enter that in by hand. But watch this, 6.02 E23 equals. Now it's in there right now. You might say, well, how do I know it's in there? I don't see it much. I see 6.02 and then I see a little 23. How do I know? How do I know for a fact that this giant number is in there? How can I tell that? Well, watch, I'll just take this number and I'll go times 10. And when I do, you should see it now says 24. 24 powers of 10 instead of 23. Can we do the same thing with our calculator app? Sure, 6.02 E23. Bam, there it is. It's in there. The whole thing's in there. And again, you might say, well, how do I know? Well, times 10. Now it's times the power 24. So you really can enter this huge number very quickly with a few keystrokes. And the way we write it is the way you put it in. 6.02, the E key, then 23, and you're done. Now, if that doesn't convince you, well, later on in this lab, the bright line spectrum, instead of doing the mole, which is used to handle a very large number of things, you might have to enter this number. This is Planck's constant, which is actually just like the speed of light here. It's a fundamental constant. It's a truth about the universe that the fastest thing we know of is the speed of light. And in a vacuum, the speed of light always has the same speed, which is 2.997 times 10 to the 8th meters a second. That's part of the physical laws. That's actually built into the standard model of physics. It's a number that crops up over and over again. Well, what is this? Well, this is not C, this is H, sometimes called Planck's constant, named after a German physicist named Max Planck, and who developed it by doing actual observations of the energies given off by the hydrogen atom. He did careful calculations and he got a number very close to this, and he called it H, and in his honor, it's now just called Planck's constant. And this also is truly a fundamental constant. It's also built into the structure of the standard model, and it seems to be part of the long-term structure of the universe. So these are actually real numbers, but whereas this number is a very relatively large number, 299 million, this is a vanishingly small number. How do I handle that? Well, I'll go 6.626 E. Now I'm going to put in the negative power, 34, plus minus key, and we get the number. Except I entered the wrong number, 6.626 E, 34, plus minus key. And now that number is in there. Let's do the same thing with our calculator app. 6.626 E, oops, we missed a digit, 6.626 E, that's the danger, 6.626 E, 34, flip the sign, and there it is. Okay, so you might wonder what this one would look like. Well, it's a 0 followed by another 32 zeros and then 6626. You can't even write it out on the whiteboard. It's not practical. Your zeros won't even look like zeros. They'll look like just little dots in order to fit them into on the whiteboard. That's how vanishingly small. And you might say, well, gosh, why do we have to use such large numbers and such small numbers? Well, I understand. I understand. These are not like the numbers we use in everyday human life. But the universe has things in it that are much bigger and much faster than everyday human life. It has things in it that are vanishingly smaller, millions and millions and millions of times smaller than everyday human life. And those are real. And these numbers, the very large, the very small, are built into the fabric of the universe. And that affects us in chemistry. And so we have to use these numbers. And so isn't it nice that we have a notation that allows us to quickly write down very large numbers and quickly enter the same very large number in the calculator? That's actually a marvelous, wonderful achievement. Okay, so let's now demonstrate the math. The math is actually takes advantage of the fact that the speed of light, again, we represent that with the letter C because, you know, it's a constant. And again, it is 2.997 times 10 to the 8th meters per second. Now, the speed of light equals what's called the wavelength times the frequency. Okay? So the wavelength is simply how long the wave is, and that number is in meters, and we represent it with this symbol that looks like an upside down Y, that's lambda. And frequency, of course, is F. Let me do that again. Okay, so once again, we're going to write down some numbers, and I'm going to write down the speed of light. We use the symbol C because it's a physical constant. And again, the value is 2.997 times 10 to the 8th meters per second, and that's a fundamental constant. Now, the wavelength we represent with something that looks like an upside down Y, that's the Greek letter lambda, and we represent the frequency of the wave as F. And so the speed of light, this number equals the wavelength times the frequency. Now, what does that mean? Well, the wavelength is in meters, literally, and the frequency is in, well, per second. Right? Meters per second, okay? So if we have a wavelength times the frequency, whatever the wavelength is times the frequency, it's going to equal the speed of light. And so here's the fascinating piece. The speed of light divided by the wavelength gives us the frequency. The speed of light divided by the frequency will give us the wavelength. It's beautiful math. It really works out. Now let's say that we're looking at a local radio station. The example I like to use is 94.9 megahertz on the FM dial. Now that's KBOS, KBOS, popular station because it plays hip hop, among other things. But when we say 94.9 megahertz, we actually mean this, 94,900,000 cycles per second. And in the metric system, we use the symbol capital H little z. It means cycles per second. That stands for Hertz, named after Heinrich Hertz, who did a lot of pioneering work with sound waves. Okay, so if this is the frequency of the wave, and if radio waves are just light waves that travel at the speed of light, then the speed of light divided by this frequency should tell us how long this wave is. Again, the speed of light divided by that frequency will tell us how long this wave is. So we're going to put this very large number in our calculator, 2.997 E8 meters per second. That's the speed of light, C. We're going to divide it by this actual local radio station. Radio is just another wave on the electromagnetic spectrum. Now, the meaning of hertz is that this is actually per second. This is the number of times the wave goes up and down per second. And guess what? Since we have per second on top and per second on the bottom, the per second cancels out. So whatever this answer is, it's going to be in meters. All right, let's do it. 2.997 E8 divided by 94,900,000. Better be careful when I enter those zeros. There it is. And here's my result. It says 3.15, blah, blah, blah. We're just going to round that to 3.16. And so the radio wave that's produced locally by the station 94.9 KBOS, the hip hop station, each radio wave is actually slightly more than 3 meters long. That's about, 10 feet long, a single wave. Can that be true? It sure is. Radio waves are relatively large, and radio waves and so-called microwaves and infrared rays, they're all larger than the waves of visible light that our eyeballs are tuned to. Of course, there's also waves that are much smaller than visible light, things like, ultraviolet, X-rays, gamma rays. Okay, so that's that. Now let's talk about the math we get from the lab. The math from the bright line simulation that builds upon this idea, that math is going to see us calculate some waves. We're going to get some numbers for different waves that come from taking samples of atoms and making them excited by running an electrical current through it. And the atoms are in the form of a gas, and the gas glows, and then we run the light from a gas through a prism, and we see the prism, the prism breaks the light waves into different sizes. And when we do that with these special samples of gas that are excited, we don't get all the colors of the rainbow. Instead, we get precise lines, which we call atomic emission spectra. Now, it turns out that when we're talking about the colors of visible light, they are somewhere in this range. They are 400 to 700 nanometers. You might say, well, what is a nanometer? Well, a nanometer is 1/1000th of a meter. You can write it like this. Now, it is an unfortunate fact, ladies and gentlemen, that if you want to be successful in doing the lab, you have to first take all the numbers you get in nanometers and convert them into meters. You might say again, well, why do we have to do that? Why can't we just measure these things in meters? Well, look, the speed of light, it's convenient to have it in meters per second. And to measure the tiny little spectra, it's convenient to use a different unit, the nanometer. But if we're going to involve the two of them together, then we have to convert one to the other. That's just the way it is. Okay? So in this case, we're going to take this wavelength and we're going to convert it into a wavelength that's, well, it's going to be a number less than 1. It's going to be a negative power of 10. So I'll do a demonstration here. We're going to go 400 times 1e9. We flip the sign with the plus minus key. And look at that. We get this thing. It's a very small number. So let's imagine we did that. 400 times 1e negative 9. And when we do that, we get 0.0000004. Well, that's correct, that many meters. But there's a more elegant way to write that. And as you might imagine, it involves scientific notation. So we count the number of places in front of our 4. And there are 7 places. And so this is this is 4e negative 7 meters. Now, if 400 is 4e negative 7 meters, then 700 would be 7e negative 7 meters. And so I hope I'm not giving away any secrets when I say that all of the numbers in the bright line spectrum lab, when we convert them from nanometers, they'll fit somewhere in this range. There'll be some number between 4 and 7 times 10 to the negative 7th. They'll all be like that, every one of them. So not really all that hard. Now the lab asks you to look at hydrogen and sodium and mercury and neon. Now, hydrogen has 4 lines, and you're going to have to plot all 4, and you're going to have 4 numbers in nanometers. And sodium has just 2. Now, I actually haven't bothered to count, but both mercury and neon have many. I don't need you to plot them all. Plot the ones that are most dramatic. But I don't care how many you plot here. There will be many of different colors. But just plot them on the paper. You won't be asked to do any math. The math will be you need to do the 4 hydrogens and the 2 sodiums. So what I'm going to show you now, you're going to have to do for 6 different numbers. First, You're going to take whatever numbers you have for hydrogen and sodium, those 6 numbers, those will be numbers in nanometers, and you'll convert them into meters. And so you will have 6 numbers, and you will have the wavelength, lambda, but the wavelength will be given in some number that's in meters. Now, what we want to do is we want to convert the wavelength of these different colored light waves. We want to convert them into frequencies so we can calculate the energy. So I want to remind you, since the speed of light equals lambda f, that means that the speed of light divided by the wavelength lambda will give us the frequency. And so that's our game. Let's pretend that I am in fact using that 400 nanometer wave, and I converted it into 4e negative 7th meters, okay? So according to our equation, c, the speed of light, equals 2.997 E8 meters per second. All right, and now we're going to divide it by the wavelength in meters, which is 4E negative 7 meters. And since the meters per second is on top and meters are on the bottom, this is all going to cancel out. And whatever our answer is, it's going to be in cycles per second, or as we like to say, hertz. Let's do that calculation. Okay, so first speed of light, 2.997 E8, bam, there it is, it's in our calculator. Okay, divided by 4 E7, it's a negative, we flip the sign. We get this, 7.4925, and the power, hard to see, it's to the 14th. Perhaps our calculator app will be more user-friendly and will be easier for us to see the power. Okay, so 2.997 E8, the speed of light, divided by 4. E key is right next to the 1. The power is 7, which is negative. We flip the sign. And then now notice what happens here. We get the first number, we get the first one, it's 7, just like before, and then we have a 4925 just before, but here, since it's giving you the whole display, we actually have to count the number of places after the first non-zero integer, which is 7. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it is 14. And I'm going to take 7.4925, and we're going to round that to 7.5, and this becomes 7.5 times 10 to the 14th hertz. So that's what you're going to do. You're going to have 6 numbers in nanometers. You're going to convert them into 6 wavelengths in meters. They'll all be negative powers of 10. Each wave, you'll use this expression where the speed of light divided by the wavelength lambda gives us the frequency, which means you're going to be taking 2.997 times 10 to the 8th and dividing it by 6 different numbers. And then you'll end up with 6 different numbers for the frequency. This is the frequency in cycles per second, or as we like to say, hertz. Now, there's one more thing that we get to do with all this. One more thing. And that is, once we know what our frequency is, we can actually calculate the energy. How? By using Planck's constant. So remember, Planck's constant is that one of those constants, kind of like the speed of light, which is built into the laws of the universe. Again, it has this very small number. It's a 6.626 e to the negative 34. The units happen to be joule seconds. Okay, and so that's Planck's constant. We use the symbol H, and you might say, well, okay, that's well and good. You showed me that before, but why does it matter? Well, see, now that I have Planck's constant, and now that I have a frequency, I'm going to lay a new equation on you. And that equation is for the energy of a photon, of a particle of light that has a particular wave, which, if it's visible light, we experience as a color. And we have this formula. It says H F. The energy of a photon, the energy of a light wave, is equal to Planck's constant, 6.626, times 10 to the negative 34 joule seconds. And the whole thing is going to be multiplied by the frequency, which in this case is 7.5 e to the 14th hertz. Let me just point out something to you. Hertz just means cycles per second. So in a sense, this is like 7.5 E14 divided by 1 second. So with a moment's thought, it should be obvious that the second that's attached to Planck's constant and this number on the bottom is going to cancel out. And so whatever our answer is going to be, it's going to be in joules. So that's our setup. And now we do the calculation. Again, Planck's constant, 6.626 E 34, flip the sign, times 7.5 E 14 equals. I get this number, 4.9695, and the power is hard to see, but it is negative 19. I'm going to set that aside for a moment. We're going to do the same piece of math here with our calculator app. 6.626 E 34, flip the sign, times 7.5 E 14. And I made a mistake, so we'll have to do that again. All right, and now let's try that again with our calculator app. We have 6.626 E 34, flip the sign. Okay, Planck's constant is in there. We'll multiply it by the size of the wave times 7.5 E, the power is 14. And there's our number, 4.9695. This is pretty much the same thing that we had here. So we'll round that to 4.97, and the negative power is times 10 to the negative 19th, which of course is very small, but hey, we're talking about a single photon, a single particle, a single light wave. And the unit, of course, which didn't get canceled, is the joules. So at the end of the lab, you will not only have 6 wavelengths, all in meters, but you will have 6 frequencies, all in hertz, by using the speed of light. And then you'll take that frequency and multiply it by Planck's constant, and you'll end up with 6 separate energies. But congratulations, you've taken your first steps into a quantum reality, because you're doing some of the equations that were developed by guys like, Planck and Bohr and Einstein and more than 100 years ago, and this introduced the field of quantum physics. And how about that?